Hello, and welcome back. In this video, I'll be discussing the arc length function. The idea here, and we'll see this in an example at the end of the video, is that while an object, two different objects could have the same trajectory, they might travel that trajectory at different rates. For example, spinning something around in a circle, you could be doing this very slowly, or you could be doing it very quickly. So it can trace out the same circle, but being at two different rates. We'll see this, like I said, at the example at the end of this. We'll see a particular version of this. And so it makes sense to study how the arc length changes, so the arc length of this curve, how this changes with respect to our parameter t, this time variable. So thinking about how the length of the curve, if we're thinking of this as position and time, how the length of the curve depends or correlates to the time that's passing. So how fast is it traveling along that curve is the idea. And that is what the arc length function gathers. So really, well, what the arc length function does is it measures how much arc length has been accrued between some fixed point A and any point in the future, t. It could also be in the past, and this would just switch. That's fine. So this is going to measure how much arc length is accrued between over the interval A to t. Right? We're integrating speed. This is like our length function, our arc length from A to t. And so now that we have this arc length function that accrues arc length as we go along, we can differentiate it with respect to time to study how the arc length of the curve changes with respect to the parameter t. That's the idea. So now we're going to hit this with a ds dt, right? Or a d dt. We're going to differentiate this with respect to time. And as you can see, that's going to involve the fundamental theorem of calculus. So it's cool to see that showing up. Right, so here we are differentiating it. It's ds dt, so it's the derivative of this integral with respect to t. And, well, it's the fundamental theorem of calculus. We get exactly the integrand, right? The magnitude of the velocity, which is speed, right? So what we get out here is exactly speed. So that is exactly how the arc length of a curve changes with respect to the parameter t, is its speed. That's what this is saying. But this extends beyond position and velocity, right? This is in general what's happening. So let's take a look at an example to kind of place this in context of some other stuff that we've seen. So here I have two different trajectories for an object, r1 of t and r2 of t. So here I'll graph r1 of t. So here's x and y. And we know this is a circle of radius 1 centered at the origin. So this just looks like a circle. But remember, it's not just the circle. This has a orientation to it, right? So I could graph, say, r of 0, I would be right here. So this would be, I'll do this again, right? This is r of 0. And then r of pi over 2 will be here. And so on, right? R of pi and r of 3 pi over 2. So I'll just graph those, and then I'll draw the rest of this in red. So the trajectory of the object, we could do all the points, all the t values in between, and what we get is an object traveling counterclockwise positively around the origin with radius 1. And that's from t from 0 to 2 pi. Here I'm going to consider r2. R2 of t is just going to go from 0 to pi. So I could plug in 0 for r2. Oops. Let's say I didn't mark my x and y here. Oops. And 1 is right there. So r of 0 would be right there. And that's exactly what, that's 1 as well, right? Cosine of 0, sine of 0, I still get r of 0. And then let's see, what's r of, what did we do? We did 0, pi over 2. So what's r of pi over 2? R2 of pi over 2. This would be what? Cosine of pi, sine of pi. Okay, so that's actually over here, right? That's -1. And then I go all the way to pi, but r of pi, that'll be cosine of 2 pi, sine of 2 pi. I'm back here at 1, 0. Right? So maybe I want to consider some points in between. How about, say, pi over 4? Then I'll get cosine of pi over 2, sine of pi over 2. I'll get cosine pi over 4 will be 1 up here. So this will be r of pi over 4. So the trajectory is the same, but it's taking half of the amount of time to make the whole trajectory around in the circle. It's going in the same direction. It's the same circle, but we're covering that circle in half of the time. So let's compare the arc lengths. What do you think? How is the arc length function for R1 going to compare to the arc length function for R2? And then how is the, what is going to be ds dt for each of these? So let's go ahead and work out. So R1 prime of t, that's what, minus sine of t. So we're going to work out the arc length function, and then we're going to differentiate with respect to t. Cosine of t. Or rather, we saw here, so this is my velocity, we saw here that if I want this ds dt, and I still want the arc length function. Let's get the arc length function. So then the magnitude of this, of r1 prime of t. So my speed is square root minus sine t squared, so that's just sine squared t plus cosine squared t. And that's exactly 1. So my speed is 1. It's traveling at a rate of 1 as I go around the circle. So that is if t is in seconds, say, and t is in seconds, and this output is in, let's say, feet, then what this is saying is that in 1 second of time, I will travel 1 foot. That's the idea. That's this arc length function being exactly 1. The speed is being 1. Okay. Right, so what's my arc length function then? So my s of t, my arc length function, is the integral of this from any point in time a to t. So if I want arc length from some point to some other point, this is just 1 dt, which is just t. So my arc length function is exactly t. If I differentiate s with respect to t, I get 1, which matches up with what I showed before. It should be exactly my speed. So this is a nice thing that's happening. This has a really nice property that its parameter t is exactly its arc length. Arc length function is the parameter t. That's really nice because that means it's traveling at this constant speed of 1 around the curve. If we compare it to this case where we did the same trajectory in half the time, let's work out everything here. R2 prime of t, what happens with the calculus? So here I'll take a derivative. That's going to be, what, minus 2 sine of 2t. And then 2 cosine of 2t, right? The speed then, magnitude of R2 prime of t, is square root of 4 sine squared of 2t plus 4 cosine squared of 2t. Well, sine squared plus cosine squared is 1. I'll have just a 4 in here. Square root of 4 is 2. So this has a speed of 2, right? It took this half the amount of time to go around the same trajectory, so its speed is twice what this one is. So now, if I want the arc length function, s of t, that's integral a to t of oh, so this is, sorry, this would have been t minus a if I want arc length. Sorry about that. T minus a. And then here, oh, sorry, I'm running out of room a little bit. It's t of 2 dt, and I end up with 2t minus 2a. And so ds dt is 2, which matches up with its speed, as it should. So this one does not have the property, right? If I consider a length of arc that occurs over 1 second in time, it'll cover 2 units of distance rather than just 1 unit of distance. This one does not have this nice property. When we work with some theoretical stuff in the next section that has to deal with curvature, so measuring the curvature of a curve, how curvy it is, it's going to be important for us to and make things a lot easier theoretically if we have our curve parameterized in such a way that its parameter matches up with arc length like it is here, rather than like it is here. So if we have a curve that's not like this, we're going to want to make some changes. It's going to involve looking at this ds dt. So for example, if I multiply r2 of t by if I change t to 1/2 t, I'll get an arc length parameterization, and it'll have these nice properties that I'm talking about. Okay, that is it for this video. What's coming up in the next one? More discussion of arc length as a parameter. I'll see you there.